The following program is brought to you by Caltech.
Good evening. My name is Tom Sofer. I'm the chairman of the Division of Physics, Math, and Astronomy here at Caltech. To remind you, the next lecture in the Watson Lecture Series will be on January 15th, 2014, and will be by Jean Emsinger, the Edie and Lou Wasserman Professor of Social Sciences. She will speak on aiding and abetting a culture of corruption. That's not tonight's talk. Tonight it's my distinct pleasure to introduce our speaker, Fiona Harrison, the Benjamin M. Rosen Professor of Physics and Math and Astronomy. Fiona received her undergraduate education at Dartmouth College and her PhD in physics at University of California, Berkeley. Immediately after that, Fiona came to Caltech as a Robert A. Millikan Research Fellow in Physics, and she joined the professorial faculty in 1995. Fiona studies the matter around black holes, gamma-ray bursts, and supernovae in radiation that we refer to as hard X-rays. On Earth, hard X-rays are used for medical imaging. Fiona is an experimental physicist who develops new and innovative instrumentation to study the hard X-ray universe. Fiona is the principal investigator of the NASA satellite NuSTAR, the Nuclear Spectroscopic Telescope Array Small Explorer satellite. This satellite was successfully launched in June of 2012 and is currently executing its scientific exploration of the hard X-ray universe, achieving a sensitivity and spatial resolution orders of magnitude better than any previous hard X-ray mission. Fiona was named one of America's best leaders by U.S. News in 2008. For her work, Fiona has received many honors, among them being named a Fellow of the American Physical Society, an honorary degree from the Danish Technical University, and most recently receiving NASA's Outstanding Public Leadership Award. Besides her science, Fiona has also done much service both for the astronomical community and for Caltech. She served on the National Academy of Sciences 2010 Decadal Review Panel for Astronomy and Astrophysics, and most recently she chaired Caltech's Faculty Search Committee to identify Caltech's next president. Oh, by the way, in addition to all of this, she teaches physics to freshmen and sophomores. And I certainly don't understand how she has time to do all of that. Tonight she's going to tell us about some of the exciting new results emerging from the NuSTAR satellite mission in her talk entitled From Spinning Black Holes to Exploding Stars, A New View of the Energetic Universe. After her talk, Fiona will take questions here. So with that, let me introduce Fiona Harrison.
Thanks, Tom. So it's my very great pleasure to be here tonight to tell you about NASA's newest astrophysics mission, NuSTAR, which, as Tom said, just launched in summer of 2012. And I'm going to tell you about some of the exciting results that we're getting from the first year in its orbit around the Earth. So NuSTAR is a high-energy X-ray telescope that is viewing the universe more than 100 times more sensitively, with images that are more than 100 times crisper, and with the ability to break up the X-ray light into its constituent colors with much greater accuracy than ever before possible. And it's NASA's smallest astrophysics platform. So it's because of brand new technologies, optics and detectors, that were developed by myself and my collaborators over the last 15 years, since I came to Caltech as a postdoctoral scholar, and also a tremendous partnership with JPL that's made it all possible. So let's talk about what is an X-ray? Well, okay, let's start with what's not true about X-rays. First, they don't emanate from this guy's glasses, endowing him with special vision, and they do not have magical cleansing properties. X-rays are electromagnetic radiation. And whenever I think about it, it never ceases to amaze me that fundamentally radio waves, infrared that we experience as heat, visible light, X-rays, gamma rays, all the same physical phenomenon, differing only in the wavelength. So if you think of waves in the ocean and you take a ruler, you measure the distance between the troughs, well, electromagnetic waves are ripples of electricity and magnetism that have a wavelength. And what I show here is what we call the electromagnetic spectrum. Here's the wavelength here. Don't worry about the units, doesn't matter. I'll just point out that here in the infrared, the wavelength is about the size of a human hair. When we get to the X-ray band, the wavelength is about the size of an atom. In the gamma ray, it's about the size of the nucleus of an atom. So we can also think of electromagnetic radiation as carrying energy, particles carrying energy, an alternate way to think about it. So we can also measure the energy of electromagnetic radiation. And again, don't worry about the units. I just want you to remember the number 10. Okay, here's 10. So 10 in some particular set of units is traditionally the dividing line between low energy X-rays and high energy X-rays. And the main difference being that in the low energy X-ray band, we've had fabulously powerful X-ray telescopes, like the Chandra Observatory you may have heard of. That's a NASA effort. Or ESA's XMM Newton telescope. These have viewed the heavens very sensitively. But above the number 10, we've only had telescopes based on pinhole camera technologies, very insensitive. NuSTAR is the first telescope that can actually take X-ray light, bend it to a point, and focus it, and therefore be hundreds of times more sensitive than the pinhole cameras that have gone before. So again, this just shows you in the green, that's the region of the X-ray spectrum that low energy X-ray telescopes have previously studied. Here's the region of the spectrum that NuSTAR is opening up for the first time. So why is it interesting to look at the universe in X-rays, in any energy of X-rays? Well, first, the hotter something is, the higher the energy or the shorter the wavelength of the radiation that emits. All right? So when we look in the X-ray band, we're looking at some of the hottest material, tens to hundreds of millions of degrees in the universe. We're also looking at regions in the universe where particles are accelerated very close to the speed of light and radiate energetically. Another thing, as Tom already mentioned, is that the baggage scanners and medical X-rays use high-energy X-rays in the NuSTAR band because they're very penetrating. Low-energy X-rays are much more easily absorbed by dust and gas in the universe. And so if you want to look at objects that radiate X-rays, even if they're behind dust and gas, which we know the universe is full of, you want to observe in the high-energy X-ray. So there are many sort of fundamental high-level reasons that we want to study the universe in the X-ray band, and in particular in the high-energy X-ray band. So being able to focus these high-energy X-rays for the first time took a lot of technology development, both brand new kinds of X-ray optics and detectors that were developed by a team of collaborators over more than a decade. And in this photo, I show you, I could spend a whole talk, by the way, telling you about the technologies. It's really interesting. I won't. I want to tell you about the science, but I do want to mention a couple of things. So these detectors here, brand new kinds of digital X-ray cameras that were developed in my labs with students, postdocs, engineers. They work rather like the digital cameras in your cell phone, only at high energy X-rays. And they use a new kind of integrated circuit, by the way, originating from the technologies that Carver Mead developed here for the first time at Caltech. So X-ray optics, I could tell you a lot about those, I won't, but just to tell you, to focus X-rays, you have to have the surfaces be almost parallel to the incoming light to get reflection. And the higher the energy of the X-ray, the closer to parallel they have to be, which requires you to have many, many shells to reflect the X-ray light. In our case, we had to have 133 shells, the thickness of a fingernail, all finely figured, smooth at the atomic level, coated with special reflective coatings. Again, all of this developed just for NuSTAR. And then we built all the instrument electronics in my lab in the basement of Cahill. And I want to point out that if there are any JPL people in the audience, no, we do not have students soldering flight hardware. That's all done by NASA qualified technicians. But it is a unique opportunity on this kind of scale, small scale mission to have students and postdocs here in the lab able to test and calibrate and work on the hardware, getting real hands-on experience with a space mission. So this is sort of unique to this kind of small-scale mission. So it was about 15 years, as I've said, from the first serious technology development to launch. And it was about 4 to 5 years actually building the mission. This picture here is a beauty shot of the spacecraft, X-ray optics here, and detectors. This is a solar panel. The spacecraft, the instrument, which was integrated up at JPL, and the spacecraft were put together at Orbital Sciences in Dulles, Virginia, driven across the country to Vandenberg Air Force Base, just north of Santa Barbara, to be integrated into the rocket that's shown here. These are the two X-ray telescopes, all getting tucked away. And then the rocket, this is an interesting story about the launch vehicle I'll tell you a little bit about. It's a very unique rocket. One of the co-inventors and now CEO of the Orbital Sciences company, Dave Thompson, he is a Caltech alum, co-inventor of the Pegasus, and now a Caltech trustee. So this rocket mounts under the belly of an L-1011 aircraft. I don't know if you're old enough to remember the L-1011. It was sort of the predecessor of the 747. So it mounts under the belly of the aircraft. This right here is called the fairing. That's the part of the rocket that the payload sits in. And I just want you to note one thing, okay? This fairing is a fraction of the length of the airplane, all right? So keep that in mind. The airplane then takes off, and in our case, in NuSTAR's case, the airplane took off from Vandenberg Air Force Base, flew via Hawaii to the Reagan test site on Kwajalein Atoll in the South Pacific to be launched. And there are reasons that we wanted to launch from Kwajalein, not having to do with the palm trees, which I heard were very nice, but having to do with the fact we can avoid radiation, trapped radiation belts. So I'm going to show you a video of how the launch works. This is not actually the NuSTAR launch. This is, I just want to show you because it's kind of cool to watch. This is the plane taking off. Here's the rocket under the belly of the plane. And there it goes.
One, drop.
And then the rocket drops and actually ignites and takes off in front of the airplane, going up and launching into orbit around Earth, in NuSTAR's case, going around the Earth once about every 90 minutes. So here's a picture of NuSTAR's launch day. NuSTAR launched at night. This is June 2012. So since it launched at night, for reasons I won't go into, there wasn't actually much to see at Kwajalein. So I decided I wanted to be in the Mission Operations Center at UC Berkeley because that's where we had all the engineering data. Okay, if you're at Kwajalein, you wouldn't really be able to see after the launch everything as the spacecraft deploys the solar arrays and starts working. So since it was a night launch, all we could actually see was there's an infrared camera watching the rocket. It's mounted under the belly of the aircraft, watching the rocket drop, take off. And then we also had earphones that we were in constant communication with Kwajalein, and we got all the engineering data. And so this is where I wanted to be. Now, Dave Thompson, the CEO of Orbital, is actually a friend of mine, and he offered me the very rare opportunity. He said, if you want, you can be on the airplane for the launch. But there was something unappealing about the idea of taking off on an airplane with a ton of solid explosive mounted to the belly that I said, I'll take a pass. And anyway, the engineering data were the most exciting to have. So my research group and my friends and colleagues from Caltech all gathered in the Meatman Auditorium to watch the launch on NASA TV. So here, so I should point out, actually, Dave Thompson didn't watch the launch at all. He says he hates launches, which I always thought was weird for a rocket scientist. But he had a good excuse. It was his daughter Maggie's graduation day from high school. Oops. So here's the launch as filmed by a student, obviously. And there we are. There's everybody in Meatman. And if you couldn't hear, he said, we have first stage ignition. It was a picture-perfect launch, got into a great orbit. Maggie had a great graduation day, although she decided to go to Princeton, not Caltech. We won't hold that against them. And I couldn't resist showing the youngest generation of space scientists on launch day looking forward to New Star's launch. This is Asher and Eden, our project scientist, Daniel Stern's kids, and my now 6-year-old, all anxiously looking forward to the launch. So personally, I wasn't really all that worried about the launch, because A, I had no control. B, I figured it's going to be over pretty quick. It'll either go up or down, and that'll be it. My fear was what had to happen 9 days after launch. Now, if you were astute, and you noticed, I think, the second view graph where I had the picture of Chandra and XMM and New Star, they look about the same length, which is pretty long. It's the size of a school bus, 10 meters. And if you remember, I told you to remember that the length of that shroud was a fraction of the length of the L1011, right? So how does that work? Well, here's how that worked. So part of New Star's design is to have a Tinker Toy-like structure made of tens of thousands of piece parts, all folded away inside something that in INT we affectionately referred to as the trash can. And 9 days after launch, a motor drives the structure such that these parts all tension and lock into place. You can see here's, yeah, good grief is right. This was, the Mars guys, they brag about their 7 minutes of terror, right? This was 24 minutes of terror. And I say terror because I knew how many times it didn't deploy on the ground and how many times we rebuilt it. But it was a picture-perfect deployment, locked into place, and everything worked perfectly. Now here, I'm just going to point out a few of the features. Here's 2 X-ray telescopes. We have 2 just to get more collecting area. We just add the images together. There's nothing magical about 2. Now, there are some consequences of flying a slinky in place of an optical bench. And that's that this is somewhat flexible and does move around. And so we have 2 lasers and a star tracker that are constantly measuring where the alignment of the telescope. And on the ground, we correct the images to go add them, to take all that motion out. That was a contribution from JPL that I think was truly a feat. So I just want to start. I'm now going to turn to the science for the rest of the talk. And I want to point out one sort of high-level view of the improvement, the vast improvement New Star is making in our ability to study the high-energy universe. So what is this? Well, this is a region around the nucleus of our own galaxy, which, by the way, happens to harbor a 2 million solar mass black hole. I'm not going to tell you anything about that today. But this is an image of 2 degrees by 0.8 degrees that was made with one of those, with the best pinhole camera-like detector telescope that's ever flown. And you can see that most it can do is sort of detect a few very bright point sources. NuSTAR, so 1 pixel in the image of this old telescope is the entire field of view of the NuSTAR telescope. And if you take 1 pixel, right, and you blow it up, we get thousands of pixels, and we can resolve for the first time diffuse emission, filaments, point sources that were all blurred into 1 resolution element for this old telescope. And so this is fundamentally changing our view of the high-energy universe. But now I want to turn to talk about the title of this talk, which is Spinning Black Holes, or at least half of the title. So let's talk about NuSTAR's observations of black holes. So first, what's a black hole? Well, very high level, a black hole is basically a tear in the fabric of space-time, where objects have become so dense that they collapse literally to a point. All right? Now, there is a region of a particular size around a black hole where not even light can escape due to the extreme gravity. So theory says that black holes can have only 3 observables: mass, spin, and charge. Now, astrophysically, black holes are not charged because all the material that falls on to them and that produces, that's there when they're produced is neutral. So really, astrophysically, they influence the universe through their charge and through their spin. Now note, they don't have a radius per se. They really think of them as points. There is this event horizon, the region from which no light can escape, which has a size related to the mass. But really, it's not a dimension. It's really just mass and spin. Okay, so how do we study black holes? You're probably thinking, if no light can escape from the regions around them, how can you possibly measure things like the spin? Well, black holes don't live in isolation. They live in galaxies surrounded by dust and gas. And the normal gravity of the black hole attracts this dust and gas, and it falls onto the black hole. There's no sucking, by the way. It's just gravity, all right, attracting the material. And when it gets very close, it organizes itself into a disk, which we call an accretion disk. And friction in this disk turns the gravitational energy into heat. Okay, so the regions near the black hole in this disk are hot, and in these regions, particles get accelerated very close to the speed of light. All right, and so these processes produce high energy, well, X-ray radiation and high energy X-ray radiation. So to explain to you how we measure the spin, I need to tell you something about what's producing the X-rays. And so here's an artist's conception. This isn't actually a picture of a black hole. This is a very nice artist's conception showing this disk of material that's swirling in, falling onto the black hole. This is sort of a depiction of this event horizon. And there are regions shown here in white. There's a region where particles get accelerated very close to the speed of light. And this acts like a source, a light bulb of X-rays, of high-energy X-rays across very large band. And this flashlight of X-rays shines down onto the disk, and we can see the reflected emission off the disk. So think of a flashlight shining on the disk, and we're seeing this reflected light. And it's the ability to study this reflected light that enables us to tell something about the black hole spin. And I'm going to explain how this works. So basically, what we aim to do to measure the spin is to figure out where the inner edge of this disk of material is, the accretion disk, all right? How does this tell us about the spin? Well, so general relativity It tells us that a particle that is orbiting a black hole has a minimum radius where it can stably orbit. And if it gets any closer to that, it just can't have a stable orbit. It just plunges into the black hole, never to be seen again, all right? Now, it turns out the location of this inner most stable orbit depends on the black hole's spin, all right? So if, let's just focus on this picture and this picture. If we have, as in the top one, the particles spiraling in, all right, in this, as shown by this white arrow, and the black hole is not spinning, then the accretion disk can come close, but not that close. It can come as close as 6. Don't worry about what 6 RG, don't worry about what RG is. Just say, remember 6. And if the black hole is spinning, let's say it's spinning as fast as it possibly can, there is a maximum spin it can have, dictated again by general relativity, and the material is circulating in the same direction as the spin, then it can come a lot closer. It can come to 1. Again, don't worry about RG, all right? So it can come much closer if the black hole's spinning. So it's by measuring the edge, the location of the edge of this disk of material, that can tell us how fast the hole is spinning. And so then how do we tell where this edge is? Well, it turns out the way we tell is we make a rainbow out of the X-ray colors. We break up the X-rays into their constituent colors, energies, or wavelengths, however you prefer to think about it, all right? And we get a different shaped rainbow depending on how close the inner edge of this disk is. So if we look here, this is energy of the X-ray. Now here's that magic number 10 I was telling you about. Remember 10? Okay, it's going to come up in a minute. And here's the shape of the rainbow if the inner edge of the disk is at 6. Don't worry about the units. If, on the other hand, the inner part is much closer, then this emission gets much more stretched out and distorted in a different way, all right? And so what actually, now if you know some physics, what is this distortion from? Well, this peak right here turns out to be from iron, the element iron in the disk, all right? And what you're seeing, you know, if you see iron particles going around, you get a Doppler shift away and towards you, and you also, general relativity says everything gets smeared redward. Due to the very intense gravity. That kind of stretches things out, all right? But don't worry, if you don't get that, it doesn't matter. All you have to note is this looks very different than that, okay? And this feature here is at an energy less than 10, so an energy where we've been able to study it using previous X-ray telescopes. So you're saying, okay, well then why hasn't this been done before? We've had low energy X-ray telescopes I've already told you about. Why is it we haven't been able to definitively make this measurement before? Well, it's because if you only have a small part of the X-ray colors to look at, you only have, you know, X-ray colors less than 10, okay? It turns out you can get a very similar distortion or stretching of the spectrum, the light, if you have the material coming very close, or if you have dust and gas that's partially obscuring your line of sight. I won't go into the details of why, but that can basically also distort this emission in a way that, if you only can see below 10, looks very similar. And this has been the source of debate and all sorts of uncivil behavior at conferences for, you know, a decade. It's spinning, you idiot. No, it's not. It's just dust, you know. And then people get all exercised about this, and, you know, anyway. So it's been a source of great controversy, let's put it that way. But if you have the high energy part of the spectrum, here's what you would expect to see from a rotating black hole. Oops. Sorry. Here's what you would expect to see if you just have dust obscuration. And the reason goes back to what I told you before about how the high energy X-rays are not is subject to being absorbed by dust, all right? But at any rate, the difference is very marked, all right? So we decided, for this reason and others, we were kind of interested in studying the dust. I personally kind of liked the dust interpretation, just to be perverse. And so we decided, well, let's look at a particular 4 million solar mass black hole in a galaxy called NGC 1365. And we'll do it at the same time with XMM here and with NuSTAR, so that we could get a whole broad range of X-ray colors and really study this black hole well. And I'm going to tell you a little bit about the story of how we discovered the result that this particular black hole is spinning very close to the fastest it possibly can. Because it's one of those aha moments that I think is very rare in a scientific career. So turned out, worked on this with a collaborator, an Italian collaborator named Guido. And Guido, no, seriously, his name is Guido. Guido was analyzing the data from the XMM telescope, and with my postdocs and students here, Dom Walton is one of them who's in the audience, we were studying the NuSTAR data. And so it turned out Guido and I were both going to the same conference, and we exchanged emails and agreed to meet at the bar at the beginning of the conference and look at each other's data. And so Guido said, well, let me show you what I'm finding with XMM in the low energy part of the X-ray spectrum. He said, so here's the data, these blue points, okay, from XMM. And he said, and I fit them with the two models. Here's the model where the black hole is spinning fast and that we have this gravitational distortion. And here's the model where we have dust and gas obscuration. I really can't tell the difference. I said, I have the NuSTAR data. And I showed him the NuSTAR data. And I said, here it is. Now, this is a prediction, not a postdiction, okay? So that's one of those rare things that doesn't happen so often. And the huge difference, like you don't have to sit and argue about this and be uncivil, right? You know, this is sort of kind of obvious. And so this particular black hole is spinning very rapidly. So this was great. We had a big press release. NASA did a huge, event. And afterwards, all sorts of reporters called me up, and they said, well, I'd like to write about this, but you never said, like, how fast is it spinning in miles per hour? And I said, well, okay. You remember I told you black holes have mass and spin, but they don't really have a radius. You can't draw a dot anywhere on a black hole and say it's moving around that fast. So I said, I'm sorry, I can't answer that question because, I explained very carefully and tried to be accurate about these things that, you couldn't say. And so they said, well, okay, well, so tell me how fast is it rotating, like in rotations per minute? And I said, well, okay, you can't draw a dot on it. You can't measure how many times it's going around. You just can't think of it that way. So, well, we have to say something. I said, well, okay, how about this? Spinning black holes, they drag the whole fabric of space-time around with them, all right? Which is kind of amazing. So if you were standing near the event horizon of this particular black hole, then if somebody from infinity watched you, they would see you rotate 15 times per hour just to stay still. I said, well, that doesn't sound very fast. I said, okay, well, try this, all right? Spinning black holes have energy. We know we can tap that energy. Okay, suppose I just took this black hole and I stopped it. How much energy would I get out? I would get out enough energy to blow the entire galaxy and unbind all the apart and unbind all the matter in it. So that led to the Doomsday Black Hole article in space.com. So, all right, so let's turn to the second part. This is the last result I'm going to talk about, and this is the exploding stars part. Now, it also happens to be our first journal cover. This is the Sedona Journal of Emergence, and it turns out one of my scientists was browsing at Vroman's bookstore in Colorado, where the astrology section happens to be right next to the astronomy section. And he said, wait a minute, I recognize this image, I made it. That's a new star press image from a supernova remnant called Cassiopeia A. And if you can't read the red writing, it says, a new view of the historical supernova remnant, Cassiopeia A, located 11,000 light years away, was taken by NASA. Inside, Cassiopeia speaks through Robert Shapiro. And I didn't actually read the article, so I don't know who Robert Shapiro is or what Cassiopeia said. But I am going to tell you about this really exciting result, where we can look at this supernova remnant in an entirely new and different way, make a different kind of image, which is actually telling us directly about how massive stars explode in supernovae. So let me start by telling you what a supernova is. So if you have a massive star, and by massive I mean 10 times or more the mass of our sun, then it will explode in a supernova. It will end its life in a supernova explosion. And we understand pretty well why this happens. So the reason why is stars are giant nuclear reactors, all right? Nuclear reactions are taking place, burning hydrogen into helium, into carbon, oxygen, nitrogen, whatever. And these reactions produce heat. And you have to have heat, otherwise the gravity of the star would just cause it to collapse, all right? So it's this heat that holds stars up. And if you look at what a massive star looks like close to the end of its life, then it looks kind of like an onion. Here we have oxygen, carbon, silicon, sulfur, and then iron in the very core. But the problem with iron is it turns out you can't burn it in nuclear reactions and get heat, all right? You can't get heat out of that. Physics tells you that. And so once the center of the star burns into a core that is iron, and that core gets large enough, the star is basically toast. It's all over because the gravity, you can't create heat to support it against gravity, and it just collapses. So the core collapses, the inner layers of the star collapse and bounce off of that, boom, get a big explosion, which basically blows out the layers of the star. The core collapses to a black hole or to a neutron star. I could tell you about neutron stars. I wish I had the time. But at any rate, the part that we're going to talk about is what's left over. So here, this is just an artist's depiction of an explosion. Don't take it too seriously. But after that explosion, basically the outer layers are expelled, and a shock wave drives through them and heats them up, and you get what's called a supernova remnant, like Cassiopeia A, like the one that talked to Robert Shapiro. So, so what's important about this whole process? Well, it's really important. It's fundamental to life, because in the early universe, we just had hydrogen, helium, and a little bit of lithium. Everything else was forged in stars or in these thermonuclear explosions that blow them apart, and the material would never get out to create planets and life unless you had these explosions, right? So, this is important. But one of the outstanding questions in astrophysics today is, how do these explosions happen? What's the underlying physics that results in the star blowing apart? So theorists have spent thousands of hours of supercomputer time trying to get stars to explode, but usually they just fizzle out, all right? Even though in nature we know that most massive stars will explode. It's a very robust process. Independent of the details of the star, this usually produces a supernova. So this computer simulation I'm going to show you is courtesy of this guy here, Christian Ott, who's a faculty member here at Caltech. And what Christian is trying to do is simulate the explosion of a star. Now, what tends to happen in these simulations, at least the ones that start out pretty spherical, is the shock. So I told you there's this bounce and a shock that has to go out and blow the star apart. and don't worry about the colors, just focus on the shape of this outside, it tends to stall. Here's a clock. This is milliseconds, 1/1000th of a second. All right, so the clock is running. This shock that's supposed to blow the star apart is stalled, and there's some magical mechanism that has to dump energy into it to make the star explode. Now, probably it has something to do with particles called neutrinos, but the problem is it's hard to get them to dump enough energy in this spherical explosion. So Christian is working on models where you generate instabilities. You get these unstable oscillations. You can see them happening here, right, that are making it very sort of non-spherical, right, bumpy. And it's these oscillations that make it easier to deposit the energy and blow the star apart, all right? So you can see then that this is sort of gone from what was something very spherical to something that's very asymmetric, clumpy. But these instabilities or oscillations are just one theory, okay? Some theorists propose that maybe the explosions are very asymmetric. Maybe they're very sort of cigar-shaped and elongated, have jets. It makes it easier to explode the star if you only have to explode in two directions, right? So maybe they have jets that sort of plow out. This can happen especially if the star's rotating, all right? And maybe that's how you get the explosions to happen. But you can see this requires very large deviations from spherical symmetry, all right? So you get these sort of jet-like features. This is courtesy of a different theorist, right? And again, let me emphasize, this is a fairly fundamental how stars explode, right? We wouldn't be here if they didn't. And decades of effort has gone into theory. So what we really need is observations to try to constrain the models. And one thing we can do is we can study how asymmetric is the stuff that's left over. So it's sort of like a bomb squad doing forensics to reconstruct the explosion. If you sort of look at the distribution of what's left over and you can back it up a little bit, maybe you can tell whether it's like a jet or more like the oscillations, more blobby and elongated. And so the way we can do this is by studying the remnants, what's left over. And these remnants, by the way, glow for hundreds to thousands of years after the explosion itself. So, you can take your time. So I'm going to start a movie that shows you how it is we see the remnants. They mostly glow in the X-ray. So as I said, the outer layers of the star look like an onion, and they get blown apart. And you get a shock wave moving out, and also this shock wave that's sort of moving much less slowly. The material expands, the shock heats it, and I told you that hot stuff radiates in the X-ray, okay? So you see these things radiating in the X-ray, and you can study the colors. Different elements glow in different colors of X-rays, and you can sort of look at what the distribution is like and see whether you can study the asymmetries. Now, again, you can do this all at energies less than the number 10 that I told you about, okay? So this has been done by Chandra. This is a beautiful image that shows you the distribution of the elements, all right? So let's see what this has told us. So here's Cassiopeia A in the element of iron. It's an element that's produced very near the core, all right? So it should be imprinting the asymmetries pretty clearly. You say, well, it doesn't look that jet-like, so maybe we can rule that model out. Well, then go to the silicon. Here's a silicon. Many people have used the distribution of silicon to say this particular explosion was like that jet model, okay? Well, there's a problem. Well, first, let's think for a minute. How can we be getting such different answers from the iron and from the silicon? Well, the answer is that I told you the only material you can see in the X-ray is the hot material. So it has to have already been heated up by this shock. And also, So the iron, you're not going to see it unless it's been heated up. So you're not seeing the whole iron distribution. You're not really seeing the asymmetries that way. And then the silicon comes from the outer layers of the star, and it can be very asymmetric because of inhomogeneities in the stuff that surrounded the star before it exploded. So it's not really a good measure either. What you really want is some tracer of the material that's synthesized near the core, so near the dividing line of what falls back onto the black hole or neutron star that the core turns into and what gets ejected out. And you want that tracer to be visible whether the material's hot or cold, no matter what. And nature has given us such a tracer. It's called titanium-44. Not to worry, titanium, you know what that is. 44 just means that it's unstable. It's produced in the explosion, and it's radioactive, so it's going to decay. And when it decays, it emits high-energy X-rays that new star can study. But we've never been able to map Cassiopeia A in this radioactive emission before, because we've never had a telescope until new star that could do it. So again, this is an unbiased tracer we can use to look at whether that explosion was like the jet, or whether it was more like the bubbly Christianot explosion, or whether it was like something else. So let's look here at the iron and the silicon magnesium. Now I will tell you, I had theorists come up to me before new star launch and said, well, it's not going to be a very interesting observation, because what you're going to see, the titanium is produced in exactly the same place as the iron. All the material's already been heated. And so you're just going to get a map that looks exactly like the iron and blah, blah, blah. So I said, fine. Other theorists told me, well, it's going to look like the silicon because my model is a jet-like model. I know it's right, and so it's going to look like this. All right, so here's what the new star map looks like. Now, I tested the observational skills of my 6-year-old Joanna. I said, Joanna, does this look like that red or that green? And she said, it doesn't look like either, Mommy. And I said, you're right. It doesn't. So here they all are together. Here's the silicon, here's the iron, here's the titanium, which is the true tracer of the symmetry of the explosion. And we've run models with the help of our theorists to reproduce this. And we think this is some of the only direct evidence to date that the Christianot type of explosion is actually happening. Because you can see it does not look like a jet. But it does look pretty clumpy, and it does have some asymmetry. So when you try to reproduce this, that seems to be the best way for us to reproduce it. One of the only real handles we have observationally on the core of the explosion. So we have to wait and see. I'm sure theorists will come up with other ways to produce this distribution. I will say I was at a conference not that long ago, and one of the people who told me it was going to look like the iron said, it doesn't look like my model. What's wrong with the data? And I said, so we'll see. But at any rate, we've got the theorists firing up their supercomputers again. So this last summer, we had a birthday party for New Star outside on the Cahill patio, near where the team watched the launch from. And I have to say, my group has been having a fabulous year getting New Star working, getting it tuned up for science, and making science observations. But I will say, something tells me there's some members of my group who are itching again to build another satellite. So here's the gang, again at New Star's first birthday party. This is Caltech group and key people from JPL, all gathered to celebrate. You can see here's one of our New Star babies. It's probably purely coincident that a number of the postdocs had babies 10 months after launch. But at any rate, New Star's in a high orbit. We have no consumables, and so I'm hoping for many more birthdays to come. Thank you.